Okay, I'd like to move on to the next presentation. Okay, the paper title is the implementation of the chaotic neural network reservoir on the TSV stacked 3D cyclic neural network integrated circuit. Okay, the paper will be presented by the Professor Yoshihiko Horio. So I'd like to briefly introduce his bio. Professor Yoshihiko Horio currently is a professor at Research Institute of Electrical Communication, RIEC, Tohoku University, Japan. He received the bachelor, master, and PhD degree in electrical engineering, all from Keio University, Yokohama, Japan, in 1982, 1984, and 1987, respectively. From 1987 to 2015, he was with Tokyo Denki University, where he was a professor from 2000. He is the honorary professor of Tokyo Denki University from 2020. From 2021, he served as the director of the laboratory for nanoelectronics and spintronics, RIEC, Tokyo University. His current research interests include neuromorphic and brain-morphic hardware systems, VLSI information processing systems based on the complex physical dynamics, and high-order brain-inspired bracelet systems with consciousness, self, and embodiment. He is currently a fellow IICE and editor-in-chief of Nonlinear Theory and its Application IICE Japan Journal. Okay, Professor Horio, please start.
Oh, thank you very much, Professor Naka. Can you hear me?
Yes.
Okay. So thank you, everyone. So I think good evening to US and good morning in Japan to Japan and Asia. Okay. As Professor Tanaka introduced, my name is Yoshihiko Horio, and I'd like to go into my presentation. So the title of my presentation is Implementation of the Chaotic Neural Network Reservoir on the TSV microbump stack 3D-dimensional chaotic neural network integrated circuit. Okay, a little bit long. So, okay, first of all, I'd like to give you the background of my research. Of course, you know that deep neural network is booming right now. During the course of the development of the hardware for the DNN, a cyclic neural network architecture was proposed, and the vertically stacked 3D integration technique of that cyclic neural network using TSV is under development, as Professor Kiyoyama presented. And also the proof of concept chip will have been fabricated. On the other hand, yet another neural network, which is called Reservoir neural network, is now getting much attention because the Reservoir neural network has a very simple structure, and simple learning rule can apply to the Reservoir neural network to get the superior time series information processing abilities. And we actually extended Reservoir neural network to a chaotic neural network reservoir, which is CNNR, to get the more the dynamics in the reservoir. So we have actually two realms of neural networks, and if we combine and integrate those two in one chip, we may open up a new realm of spatial temporal processing paradigm. Those are some examples of that paradigm. This is the most simple one. We use the Reservoir network as the final stage of DNN. This may improve the DNN. Note that the DNN is usually large and complicated, but the Reservoir is very tiny and simple, so that we can use the some area, little area on the chip. Okay, and this one is we use two of them in parallel and put the same input to those networks, but after that we can get a different feature of the spatial temporal input, pattern processing, temporal processing. In addition, if we use another neural network to combine those output, we will get some result for spatial temporal processing output of the spatial temporal input. So this may give us a new novel spatial temporal integrated processing machine. Of course, other combinations are possible, but anyway, the integration or combination of those two will have some advantages. So in this paper, I will show you the implementation technique of the chaotic neural network reservoir on the cyclic DNN architecture to make those combination possible. Okay, this is the concept of the cyclic updating neural network architecture already presented by Professor Kiyama. This is originally designed for multi-layer neural network such as DNN. We have only two physical semiconductor layers here and here, and we use two layers alternatively cyclically to make a virtual layers as many numbers as want, like this. And if we change the direction of the rotation like this, this will give us a backward processing that this can be used as a forward inference and backward learning. Okay, this kind of system may give us the compact and low power implementation. However, it will be some kind of slow because of the cyclic update. These features actually matched very well to edge computing hardware. On the other hand, Reservoir neural network we have here, the typical structure of the Reservoir neural network is like shown like this. Usually 3 layers: input and reservoir layer and output layer. And neurons in the reservoir layer are connected randomly with fixed weight value. And also the connection weight from the input layer to the reservoir layer is also random and fixed. However, the connection from the reservoir layer to the output layer, here red arrows, are modified according to the very simple learning rule. In this case, this is just the 1 layer neural network, so the linear regression algorithm is sufficient. And because of dynamics in this recurrent neural network, this reservoir neural network is very suitable for dynamic time series processing. And also the, as I said before, that the simple learning rule algorithm is sufficient. So from the hardware point of view, this random connected with fixed value, and also actually that connection are sparse, usually less than 10% are connected, and the simple learning algorithm. Those are very good ingredients for the hardware implementation. So currently, many researchers are now working hard for the hardware implementation of the reservoir neural network. Okay, so one condition for the reservoir network work fine, that means stable and consistent processing, is so-called echo state property, ESP. I don't want to get into this detail, but in short, the network should be asymptotically stable for the processing. To guarantee this property, we usually set the spectral radius W. W is the connection matrix of the reservoir neural network, less than 1. However, sometimes we need some more complex dynamics for more intelligent time series processing. So we want some sensitivity and complexity rather than stability and consistency. This usually those features are given by chaotic dynamics, And actually, it is very easy to introduce chaos in Reservoir like this. Just break the echo-state property. We set spectral radius larger than 1. So to do this, by doing this, instability of the network induces chaos. This is very easy. However, sometimes we need both properties: stability, consistency, and sensitivity and complexity together. So how do you get those at the same time? So we proposed the chaotic neural network Reservoir to do so. As you see, this is the structure of the chaotic neural network Reservoir. And as you see that the structure is the same as before, but the only difference is the neural model we use, which is chaotic neural model, okay? And so the global complex chaotic dynamics on the network level can emerge by local small chaos in each neuron. So we don't have to destabilize the network itself. So we can keep the echo state property of the network itself, but we can introduce the chaotic dynamics into the reservoir layer. So we can get both of them. The key point is the, for example, key parameters K and alpha and epsilon. Those are key parameters for chaotic behavior. But if, for example, if we set K equals 0, then this equation reduces to the ordinary neural model used in the, for example, in the DNN. Okay, why we use chaotic neural network Reservoir? This is actually a rough test of the Reservoir. We use a word recognition. Data set is taken from speech spoken digit data set from NII. And we use 0 to 9, actually 10 digit in English utterances. And we made the Reservoir with 200 neurons here, and inputted 12 neurons, and those the neurons, the weight among those set randomly, and weight values are fixed. So we didn't any optimization for the network. And then after that, we put the 10 neurons for each utterances, 0 to 9. And 0 to 9 utterances were learned by the linear regression. Because of the no optimization, that the usual neuron shows average recognition rate about 40%, not good. But we fix we use the same weight matrix when we just change the neuron as a chaotic neuron, swapped. Then we got the much better performance. So maybe chaotic behavior is very good. And we changed the number of neurons in the reservoir from 50 to 5,000. And blue are the results from the chaotic neural reservoir, and the orange gives the ordinary reservoir. As you see, the chaotic neural reservoir is much better than ordinary one. And also, we can notice that the small reservoir works very fine, actually better than this. So this is very encouraging that the CNNL shows better performance with less number of neurons. That is, CNNR is a very good candidate for the edge hardware. Actually, we can put the small circuitry within the DNN, large DNN hardware. Okay, however, we have a problem, okay? Because the original cyclic updating scheme is designed for DNN. In the DNN, usually neurons have no internal dynamics. However, our chaotic neural model has internal dynamics. For example, this is a K I explained before. So this is the exponentially decaying internal state factor. Output is here, internal dynamics. So to handle this, we need special care with in the cyclic updating scheme. So we proposed the internal state copying technique. Here, we copy the internal state itself directly to the next step by multiplying the decaying factor K around here. So this is the external path, additional path to the usual, path to the neural network. This is the output. This is the internal. So this is different. So we add little trick to this circuit. This is the layer 2, layer 1, and here we add the bypass circuitry through which we can directly access to the internal state of the former neuron, actually to copy the former neuron to the next neuron directly. So we made a tag chip, and we fabricated the tag chip, and we made a cyclic chaotic neuron circuit out of this circuit, and we got a nice bifurcation diagram of the cyclic chaotic neuron circuit. So we confirmed that the cyclic updating with internal state copying was successful, but we needed some circuit modification for more performance. So the proof of concept chip were designed as Professor Kiyoma mentioned. So I will skip this. And however, we measured the chips using this kind of board. And using the measurement result from the chip, we built full circuit emulator on MATLAB using those data. And those MATLAB emulator includes almost all of the circuit characteristic of the actual chip. So we now evaluate the system and our algorithm. Okay, so first of all, we measure the bifurcation diagram of the internal state of the cyclic chaotic neuron circuit. So this is one neuron like this. So this shows much better than the before. So then we connect two neurons, and we observed the phase portrait of the output plane. X1 is the output of the first neuron, the second neuron, and we get, for example, this is torus attractor, and when we change the external bias, we get a chaotic attractor like this. So so we are confident that the proposed proof of concept chip works fine as the cyclic updating chaotic neuron. So we put 16 neurons together, connected in randomly. Connection rate was 22%, and we prepare two output neurons, S and L, and connected the neurons, full connection to the reservoir neurons. That means 16 connection to each. And we apply sine waveform and logistic function waveform. This is chaotic waveform to the input, and the network run those waveforms for 400 steps. That is this at exactly this length once. And after the learning, we put the input design logistic concatenated waveforms. And as you see, the neuron S is actually distinguishes the sine wave here. And neuron L shows that this is a chaotic logistic waveform here. So this is the transient time, but we very success to learn that. Okay, so we move to the discrete word recognition, and this time we use the same set of the data set, but we use only 2 words, 0 and 1, instead of 0 to 9, because we have only 64 neurons in the reservoir here. Okay, again, the network is neurons are connected randomly with 22% connection rate. And this time, input to the reservoir neuron, we have connections of only 6% random connections. Again, we have 2 neurons, 0 and 1, as an output layer, and those neurons are connected mutual inhibition like this. So the network runs 0 and 1 with a linear regression for 10 times, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, like that. Then after that, we input the sound waveform like 0, like this is 0. This is an actual input to the reservoir, and those outputs of the neuron 0 and 1. Okay, so here the input comes, then the neuron, which should be show this is 0, goes up, and finally neuron 0 recognized as 0. And similarly, that if we put the 1 here, actually the initial condition is determined by the noise. So this is happened to be a 1 from the first time, but here some activity goes on, but finally this recognized as 1. Actually, we tested for 2, 0 and 1 10 times, and we got the 100% recognition rate. So we are going to now extend to the 0 to 9 or other tolerances. Okay, let me conclude my talk. We proposed the implementation technique of chaotic neural network reservoir neural network in a cyclic DNN architecture, and proof of concept chip was measured and evaluated, and based on the measurement, we made a MATLAB circuit emulator. And from the MATLAB circuit emulator, feasibility of the chip and also the proposed implemented technique was confirmed. And as a feature work, we will complete the 3D stacking, actually almost complete right now, but we will measure that resulting stack chip. And that's all. Thank you very much.
Thank you, Horio Sensei. So the paper is open for discussion and question. If you have any question, please use chat window or the raise your hand in the Zoom. Is there any question? Okay, I have a question. So,
thank you.
I'm not so familiar to the this chaotic neural network reservoir.
Yes.
So, so this is a very basic question. So,
yeah.
Regarding chaotic neuron, you said. So, is chaotic neuron does chaotic neural network reservoir requires any special hardware devices? Or
No.
Is the computer same?
Very much same, because we just reuse the circuit that Professor Kiyama presented, the same circuit. So we don't need any special, just one thing is we just add a bypass connection here.
Okay.
That's it. That's it.
Oh, it looks simple.
My mic. slide doesn't go in your,
Okay.
I see. Sorry. Oh yeah, coming. So the bypass connection are here. Yeah. So
Okay, so I have one more question. So
Yeah.
is that okay? Okay, so and is there any drawback
mhm.
in CNNR compared to the conventional reservoir network?
That's a good question. The problem is that we don't know yet how to tune the parameters.
Uh,
Okay, so because of the dynamics very complex and high dimensional, it is very difficult to decipher what dynamics is important for what kind of task. So as I said, the parameter k and alpha and epsilon are the hyperparameters. That means we need to select carefully. So we are still working on the analysis of dynamics and the relationship, the dynamics and the performance of the network by using some dynamical systems theory or something like that. Yeah.
so in your verification of the CNNR, you use the 10 times 0.00111.
Yeah.
And that's how can I say, leaves the more than 70% rate. So
Yeah.
if there are more, how can I say, learning more than 10 times,
Yeah.
so the percentage will increase.
I think a little bit increase, but I think key is the a parameter. So as I said, the hyperparameter is the key. So if we want make more performance, we should tune the parameter. And now we have, let's say 10 digits, but if we have the 1,000 words, then we need to increase number of neurons in the reservoir.
Okay.
So
We have a question from the audience. So what are the long-term goals for this neural network?
Okay. Oh, that's a very good question. Actually, this is from the different level of the interest. Actually, we are. Oh, let's say, how do we are working on the how to implement the high level performance of the brain into the silicon or hardware. For example, the consciousness or the self or something like that. So we need some complex dynamics and consistency together together. So we our final goal is to make more human-like AI out of this. But the short goal of this is to combine the DNN technique, which is actually the pattern recognition, basically, and the CNN, which is not let's say reservoir neural network, which is actually the dynamic network, together to extend or the application of the neural network based AI. So we have two short goal and final goal, I think.
Okay.
Okay. Sorry about. If you are interested in that, I can talk to maybe hour.
Okay. So is there any question? So it's time to finish. So thank you, Horio Sensei.
Thank you very much.
I'd like to finish.